Welcome you all. In this session, we are going to derive the output equation for single phase transformer. The equation which relates the rated KVA output of transformer to the area of core and window is called the output equation. So the equation that relates the power rating with the main dimensions of machine, we call it as the output equation. In transformer, the output KVA depends on flux density and ampere turns. The flux density is related to core area and ampere turns is related to window area. So we have two area, one is core area and window area. The flux density depends on core area and the ampere turns depends on the window area. The simplified cross-sectional view of core type and shell type single-phase transformers are shown in the foregoing slide, and the low voltage winding is placed near the core in order to reduce the insulation requirement. The space inside the core is called the window, and it's the space available for accommodating the primary and secondary winding. The window area is shared between the winding and their insulation. So now let us see how the cross-sectional view for core type and cell type for a single phase transformer will be. See here, you can see the cross-sectional view of core and shell type transformer. The first one is core type and the second one is shell type transformer. So here always you can see here, that is what I mentioned in the previous slide. So the low voltage winding will be nearer to the core. See here, the low voltage winding will be always nearer to the core, whereas the high voltage winding will be away from the core. Okay, so this is what we call it as core. This is the core of core type, and this one is shell type. Okay, so the output equation, the induced EMF of transformer is given by E is equal to 4.44 F5M T volts. The EMF per turn is given by ET is equal to E by T. Therefore, ET is equal to 4.44 F5M. This T get cancels. The window in single phase transformer contains one primary and one secondary winding. The window space factor KW is the ratio of conductor area in window to total area of window. So this is the expression for window space factor KW, conductor area in window divided by total area. So AC divided by AW. So the conductor area is given by AC is equal to KW into AW. This just I have rearranged the equation to get AC value. The next step, the current density. Current density is same in both the windings. So it is represented by del, which is equal to IP by AP. So current density means current by area. If I am calculating it for primary, then it is current through the primary winding divided by the area of primary winding, cross-sectional area of primary winding. If I am calculating it for secondary, means I need to consider the secondary current as well as the cross-sectional area of secondary winding. So that del, as I told already, the current density is same in both the windings. So the current density in primary, that is IP by IA, is equal to the current density at the secondary, IS by AS. So I am equating these two, which is equal to del. That del is nothing but the current density. So area of cross sectional of primary conductor is AP. So from this I am getting the value of AP. Similarly AS. So AP is equal to IP by del and AS is equal to IS by del. So I have obtained those two values. So now, if we neglect the magnetizing MMF to the primary or ampere turns is equal to secondary ampere turns. Therefore, the ampere turns AT is equal to ampere turns is current into number of turns. So if I am calculating it for primary, IP into TP is if I am calculating it for secondary, it is IS into TS. That is primary means the primary current into primary number of turns. If I am calculating it for secondary means the product of secondary current and the secondary number of turns. So as I told, it is equal. So if we neglect the magnetizing MMF, it get equal. So I'm equating both of them, and which is equal to 80. 80 is nothing but the ampere turns. The total copper area of window is equal to copper area of primary plus copper area of secondary. So now you are going to calculate this. Copper area of primary is nothing but number of primary turns into cross sectional area of primary. 80 into cross sectional area of primary, and the copper area of secondary is nothing but number of secondary turns into the cross sectional area minus section of secondary conductor. So this is how you are going to calculate the total copper area. So I have substituted. So the number of turns is TP into AP plus TS into AS. Just substitute the value of AP and AS which you have obtained in the previous step. So AP is nothing but IP by del and AS is nothing but IS by del. We obtained these equations in the previous slides. Hope you remember. Just I have substituted those values. So here 1 by del is common in both the terms, so I am bringing it outside. So 1 by del into TPIP plus TS into IS. So I am getting this expression. So TPIP and TSIS is nothing but ampere turns, right? So just I am resubstituting it. So I am getting 280 by del. On equating it with the previous equation, KWAW is equal to 280 by del. From this 80 is equal to half KWAW into del, and now comes the KVA rating of transformer. KVA rating Q is equal to V, voltage in primary, current in primary, into 10 to the power minus 3. So VP is nothing but EP into IP into 10 to the power minus 3. Now I'm going to substitute the value of ET. ET is nothing but EP by TP, and AT value. I'm just substituting these two values. I'm getting AT into 10 to the power minus 3. So on substituting E and AT in the equation, I am getting that Q is equal to 2.22 F BM AI KW AW del into 10 to the power minus 3. This equation we call them as the output equation of single phase transformer. So we can state that the output equation of transformer Q is equal to 2.22 F BM AI KW AW del into 10 power minus 3. And here one more thing you need to remember is where BM is nothing but phi m by AI, phi m by AI. If you want, you can express the previous step also, 2.22 F phi m KW AW del into 10 to the power minus 3. So you can use both the equations. These two equations both are same, just you can use any one. So you should remember any one of the equation. So that's all about the output equation of transformer. Thank you.